Now, lines approach is very different from the field approach. The field comes out of lines, but when you say this charge produces a field here and this charge produces a field there and then this charge produces a field like this, the net field here is in this direction, is the sum of these fields. We call this idea superposition, right? Each charge produces a field and you just add up all of them together. But then this line was produced by this charge. But the field here, if I look at the field here by taking these two lines and looking at the density, now the density that you get will give you a field. Now do you think that this field is the field of this charge? No, right? Because if I took this line, actually the field line should be that way. But look at how it is pointing. So this field might have been what you found from the lines that came from here. But the field is the net field. It is already superposed. Remember, if these lines would have not been bent if this charge wasn't there. So who bent them? This charge. Who changed the density? This charge also, right? So therefore, the field here has already incorporated that one. So that what we understand here is to keep in mind that field lines gives you an already superposed result. You cannot say, I will do field lines, find the field with this flux divided by area, and then I will also superpose. You can't do that because it's already superposed. Okay, but that's great because then you don't have to do this vector addition. So field lines gives you a final answer. It tells you what is going to happen after everything is already interacted. Field tells you what each charge does and then gives you the final answer. The field that you are calculating here is the result of the field line doing all this. But why did the field line come like that? Because of this charge. So this is the superposed result and that's useful to keep in mind. So for Faraday, the field line approach did two things. It made it local. This guy produces lines and the lines go wherever. Now what happens to that line there? This charge doesn't control. Other charges control. Okay. And whatever happens there locally happens there. And because of that, it will locally affect a new charge that comes in and that charge will feel a force. So this is the way he thought. It was entirely local. Today, of course, because we find it a little harder to calculate with this, we use the idea of field. Because what we have done is to just take from Faraday this idea and instead we now say that it's not really local because this guy is now going to put in billions of arrows. It is local for the force. It is not local for the field. These arrows are not local anymore because this arrow was produced by that guy and it is not like an arrow actually traveled out. It's a different arrow, different arrow, different arrow. It is not like this arrow moves there. Okay, whereas this line does move there. It is that line. So I hope it's clear how Faraday thought about this. Now let us understand whether a charge will move along a field line. If I had a positive charge and the field lines were all like that, you have a positive charge here, let us say at rest, it would move here and then it will feel a force this way and it will move there and it will move there. So it looks like it's moving on a field line. If it was a uniform field like this, you leave a positive charge here, it's going to feel a force this way and it will keep moving. There it will feel a force that way and it will keep moving. So it again looks like it is moving on a line, right? If it was left at rest and the field lines look like this, like a straight line, yes, it will move along the line. But if it was not at rest, for example, suppose it had a velocity, then it has a force in this direction. That means it has an acceleration in this direction, but it has a velocity in that direction. So what do you think is going to happen? It's going to basically move like this. It's going to cut across field lines. If it had a velocity like this, this only produces an acceleration. So therefore, it's actually going to continue moving because it's going to move to the next point, right? So does it have to move along a field line? Really, no. But you may think, wait. If it was at rest, it might move along a field line. Not really. So now let us take a point charge and place it here. So if I place the charge here, you know that this must be the direction of force, right? but this is a line that is bent like this now. So because the direction of force is that way and there is no velocity, it has an acceleration like this, so it's going to gain a little bit of velocity, like you know that v equals u plus at, u is 0, so plus at means it's now going to have a velocity in this direction. It will also move like this, so now it's going to probably be here, but it has a velocity in this direction. Now at this point the acceleration is like this and the velocity is like this, but it's going to therefore go here and the velocity may bend out like this, because acceleration bends velocity. So this velocity may bend like this, but the position where it is going to go is no longer on this line, because as it gets a velocity, it's actually deviating away from the path. So after some time, it's probably going to be there, it's going to move in this path, whereas the field line, right, was like that. So is it necessary that a charge must move on a line? Well, first of all, if it had a velocity, even if it was a uniform field and it had a velocity like this, obviously it's not going to move along the line. If it does not have a velocity, that is, you place it, for a very short time it's going to move just along the line tangentially, and then after that it's going to deviate. So ultimately, will it move along the field line? No, right? So unless of course it is a straight uniform field like this, let's say, need not be uniform, as long as the field lines are all straight, then if you place it here and at rest, it will obviously start moving in that direction. Okay, like radial field lines for point charge, it will move along the radial line. But there are very few cases where it will actually move along a field line. Field lines don't tell you how the charge moves. Field lines tell you what is going to be the direction of the force at that place. Okay, so these 3 points, let's come back and keep that in mind. Charges, positive charges produce lines. How many lines? I am going to pretend that the number of lines is q by epsilon naught. That's not normally accepted, but you will find that it's very useful for calculations. Okay, so negative charges take in lines. How many? Depends on the size of the charge. Double the charge, double the number of lines. Double the number of lines it will pull in. If you double the positive charge, double the number of lines that it produces. Lines do not cross or touch each other. Lines try to be as far away as possible. So that means lines try to keep a distance, and we will see that that's very, very critical, because that's what will allow us to calculate field. Once you know the distribution of lines, then the number of lines in some area divided by the area, the density of lines tells you the magnitude of the electric field. And what about the direction of the electric field? That is going to be the tangential direction to a particular line. If you say it's very close to a particular line, then the direction will be tangential, right? I hope this is clear. So let us use this to compute, because lines directly do not lead to numerical or quantitative calculations. It gives you an intuitive feel. Like you can look at this and you can say that, well, this seems like it's going to come together, because that's what the lines are doing, right? They're coming here. Whereas if you take two positive charges, it looks like they're pushing away. Now these are all very qualitative statements. Ultimately in physics, we would like to do it quantitatively. This seems like a quantitative approach. Today what we are going to see is that we will use the idea of lines and try and see whether we can quantify it by just using lines, whether we can calculate things like electric field very, very simply, and we will find that that is really true. And it is not true for all situations, but for many symmetric cases. Okay, so let us try and do it in a couple of situations, then we will understand it better.